So as Joe said, I'm from Northern Ireland. I'm also the lead geologist of Project Inner Space, and it's a non-profit whose mission is really to unlock global growth of geothermal through the transfer of resources, the transfer of resources, technology, and know-how, mainly from the oil and gas industry into geothermal energy production. And that's where my background comes in. As Joe mentioned, I've 20 plus years experience, and most of that had been within oil and gas. And one of the platforms that we have developed to help achieve our mission is a geothermal opportunities map, or GeoMap for short. And that's essentially what I'm going to be talking to you about today. And I'll focus a little bit on the research behind the data layers that you can see in the GeoMap. And just on your screen now is an image captured from the online tool. We launched it back in December at COP, at Bill Gates Climate Forum, which was very exciting. And it's free and online, and anyone can access it just by visiting the Project Inner Space website. So if you haven't seen the tool, and you haven't played about with it, go online now. You can go on when I'm talking and you can click on the different layers that I'm going to be talking about today. And the tool's been developed in partnership with Google, and they bring to us a lot of surface data and surface knowledge into the platform. And the role of Project Inner Space, and particularly my team, is to bring the subsurface knowledge to the platform. And within GeoMap, there's a whole body of work. It's essentially 4 modules. One relates to the surface, so the demand for geothermal energy at the surface and the restrictions, legislation, protected areas, all of that's in there. The other is the subsurface module, which is kind of my baby and what I'll be talking about today. There's also a suitability analysis tool where we bring our knowledge together in relatively simple weighted overlay analysis to look at geothermal favorability globally. And coupled with that is a techno-economic sensitivity tool that we call TEST. And all of this work is designed to be integrated together to provide a number of outputs to a selection of user inquiries about geothermal resources and its development potential. So the main thing is go in, have a play about with it. So today's talk will focus on the subsurface because that's my background. I'm a geologist, a basin modeler now of 20 plus years, and all the projects that we'll talk about today are actually projects that we fund to create new data to help deepen our understanding of geothermal potential anywhere. So I'm going to share some of that with you today. So I'm clicking a lot of things, so let me know if somebody pipe in if I haven't clicked on. So we're going to start with some basic terminology, and this is just to make sure everyone's on the same page because there's a lot of different terms that get thrown about for the different layers of the earth. But I'm going to talk about these layers and why they're important to heat flow. So we know that the earth, since its formation, since the Big Bang, has been in the process of cooling down. And it does this while it also generates new heat from the decay of radioactive minerals. And the way the earth loses heat is actually quite similar to how our bodies lose heat and release heat. It's not equal anywhere. There's certain places that it releases heat more than others, and we can measure the variation in the loss of heat at the surface. And what we fundamentally measure at the surface depends on the contributions in the transfer of heat through 3 different layers: the mantle, the crust, and the sediments. And a lot of our research focuses on understanding these layers in more detail. So the mantle is important, and most important actually in conventional geothermal systems. How we understand the contribution from the mantle is by defining the depth of the lithosphere asthenospheric boundary, and that's lab for short. So if you hear me talking about lab, that's the layer I'm talking about today. And to a basin modeler like me, the lab represents to me an isotherm. It's the temperature at which melt occurs. And it's often quoted in the literature as being the 1330, so 1330 degrees centigrade. So in old stable cratons where the crust or the lithosphere is thick, the lab can be very, very deep at a depth of 250 kilometers. And these areas tend to have very low surface heat flow. The lithosphere is thinner in newly formed oceanic crust, and the lab is elevated. And we know these areas tend to be hot. So you can understand why the knowledge regarding the position of this boundary is really critical to us in our models. Crustal thickness is also important. The thicker crust generally results in more heat production due to the presence of the radioactive isotopes. So this is where we create heat, and it's the decay of uranium, potassium, thorium, particularly in the very uppermost part of the crust. And the amount of decay there really depends strongly on the geology. So in areas where you may have thick granitic crust, up to 50% of the total heat flux in that area may come from radiogenic heat production. Now, the sediments we call the tertiary contributor. They have a much lower contribution, but radiogenic heat production still needs to be considered, particularly in deep sedimentary basins. So this is more important offshore, where you have thick marine shales, and actually those marine shales can generate significant amount of radiogenic heat production. Now, what we have to balance in our models is that the thickness of that sediment and crust also influences the transfer of heat. So as thicker crust and sediments can act as blankets or insulators and affect the rate at which heat from the mantle is conducted to the surface. So there's a real balance that we have to play here between producing heat and transferring heat. And we need to account for all of this actually within our models. And that's really what phase one is about and the objective of our research program. We need to understand these layers. And what we're looking for really are where the layers are thin and heat loss to the surface is greater, making it more accessible to target higher temperatures at shallower depths, or where we have very thick granitic crust and high radiogenic heat production. And you can imagine these layers in the same way as we wear clothes. In places where the Earth's layers are thicker, and such as when we wear a big winter jacket, we don't lose heat. Where the layers are thinner, such as a nice light t-shirt in the summer, heat can escape. So these layers are simply the clothing that the Earth wears. And in thinner the clothing, more heat escapes. So that's essentially, fundamentally, what we're trying to establish in our phase one research. So let me click. Hopefully you can now see a triangle. And our research program that we designed includes 7 funded projects, and it employs 85 scientists globally. It was designed to provide that fundamental knowledge and create what we call a robust base to the exploration triangle. And that's the triangle that you see in your screen in front of you. And the reason we do this is to facilitate decisions on where future efforts and resource should be focused. Because once we move up the triangle, it becomes more time consuming, more expensive, and more data heavy to understand play, fairway, and prospect analysis. So we want to home into the areas that are worthy of spending that time and resource. And by establishing a robust base, that helps us make those decisions. And what you gain access to on the GeoMap Beta platform online is essentially the data that we have created from the first 2 layers of this triangle. And those 2 layers are slightly different, actually. The first base layer is really about things that we can't see, and it often requires geophysical methods and associated modeling to understand. The next layer up is more observationally driven, and you can see it on the surface. Some of these things, such as the volcanoes, geysers, igneous features, faults that are moving, or you might be able to see or observe through seismic, EM, or even penetrate by a well. So we call these more observational top-down, and the base layer more modeling bottoms up. But coupling both these together is where we get to understand where areas are favorable for geothermal. You do one in isolation and you can miss out on areas. So it's really, the power is in coupling these 2 approaches together, that bottoms up with the tops down. And what I want to show you today is firstly, how we're approaching this in terms of our research, but more importantly for you guys, because we're in Northern Ireland and I'm from Northern Ireland, is how do we use these different layers to understand the geothermal potential in Northern Ireland. So we'll end the presentation with a little bit of a case study into Northern Ireland. But before we get there, we want to talk first about the layers, and we'll start with the lab. And because this really, in many ways, is the most important, but the hardest to define. And we've mentioned before, it's a significant transition zone within the Earth's mantle, and it's characterized by a velocity contrast. So where seismic waves essentially slow down as they pass from the rigid lithosphere into the more ductile asthenosphere. And by analysing the velocity of the seismic waves, we can identify the depth of what this transition occurs. And the technique relies on seismic, which is also called seismic tomography. You might have heard that term. It uses seismic waves, including shear waves. And the analyzes basically the travel time and the propagation, the path of those waves. And the source of energy is normally from earthquakes or artificial sources that exist. And the map that you see on the left-hand side of your screen, the lovely colorful map, highlights S-wave velocity deviations from a regional average. So we plot these against what we expect the average to be, and we always plot it at a certain depth, and the depth displayed here is 110 kilometers deep. Now, the dark purple that you see in that map indicates colder, thicker lithosphere, and you can see how beautifully, if you know your geography of Africa or your geology of Africa, how beautifully that Pan-African fold belt and the Congo Craton stands out in the map. And actually, I don't know if you can see my mouse, but I'll highlight those here. And the map on the right-hand side is the depth to the lab. And you can see the very positive correlation between these two maps. And if you recall, in our previous slide, we mentioned that the lab represents that 1330 isotherm, the temperature at which melt occurs. So it's no surprise when you look at the shear wave velocity in the lab map that there's a really strong spatial correlation between those colors where the lithosphere is thin and active quaternary volcanoes. And they're displayed here as little tiny red triangles, and you can see them in the orange and yellow zones. And almost 80% of active volcanoes occur in these orange and yellow zones or in thin lab anywhere globally. So it's really, really important to understand where this is. And you can see not all these are known geothermal zones. This one shows up beautifully, the Benue Trough in Africa between those two cratonic fold belts. This isn't a very well-known geothermal region, but there's some incredibly high temperatures here because there's a shallow asthenosphere. So for all the geophysicists on the call, you know that converting wave travel time and propagation paths to depth is not without complexity. And determining the absolute thickness of the lithosphere is incredibly difficult. And this is particularly true in Africa, more so than in the North American cratons and the Australian cratons, which are very large, but the African cratons are actually relatively small in terms of global craton size. And this creates quite a number of significant edge effects around them. And these are difficult to resolve. So you can imagine how the way to process the data around these cratons. So we have funded a group in Cambridge led by Sergei Lebedev to help reduce the uncertainties around the thickness of the lithosphere. And we're tackling it in two ways. The first is we increase the frequency and the resolution of the global seismic tomography database. And this is something this group has been doing for 20 plus years now. They're one of the leading groups in collecting tomography data. And the second is that we'll be providing more accurate information on the lateral and vertical heterogeneity of the crust, of the bulk crust, including its density, dictated in part by its facies, and this all helps to improve the velocity model. So we're really homing in and trying to refine the position of the lab because we recognize that it's fundamentally dictates the mantle heat flow, and that's really, really important for geothermal. So in the same thread, hopefully now you can see crustal thickness, we're doing the same for crustal thickness. And we mentioned earlier that the crust is important for three key reasons. One, it helps to understand the radiogenic heat production, particularly in that upper part of the crust. But the thickness and variations are also an input into the velocity model to help invert the shear wave data. And then thirdly, the crust can also act as that insulator. So it's important to understand its thickness and the conductivity for the heat transfer process. So to gain a better understanding of the crustal thickness, we've been collaborating again with the University of Cambridge, but a slightly different group, who have produced a new global crustal model, and it's called ECM1. And the results of this have been published for the first time ever, actually, in GeoMap. And the model boasts really an impressive expanded database in terms of crustal thickness measurements. There's over 26,000 spot measurements of the crust. And they primarily come from seismic data. Some of them are well data or gravity inversion data, but mostly from seismic. And importantly, it includes seismic velocities within the sedimentary cover, the crystalline cover, and the uppermost mantle. So it's actually critical for understanding the variations in the composition of the crust, which feeds back into our shear wave inversion. So what I hope you get here is a picture of, while we have these isolated research projects, they're all designed to be integrated to improve and refine a lithosphere model. So in that thread, we mentioned that crustal facies is important as crustal thickness. And this is because the facies constrains both the radiogenic heat production and the conductivity, which dictates the heat transfer through the crust. So we have, to understand facies, another research program, this time with a group of structural geologists called Tecton No and Knowing Earth, Doug Payton and his team, and to build a structural and tectonic database. And loads of different data sources are used to build this data set, including Landsat, radar, gravity, magnetic data, the same types of data that was acquired during the TELUS survey in Northern Ireland. Most of these sets are publicly available, but what we're doing is analysing and interpreting these to build up a structural and crustal model that also includes igneous interpretation. And that's really, really important for geothermal, that we include the igneous activity within our facies model. Where available, we'll cross-check our models with seismic and well data. And there's also this vast library of secondary information within published literature. And what we're using that data set for is to gain more insight about the features of the age of the features, such as the fault, how deep the faults are cutting, what the activity is in the faults, but also the composition of igneous rocks. So the approach we have taken is really powerful for places like Africa, because it allows us to build a tectonic and crustal fabric anywhere, even in data poor areas. And the slide shows an example from Northern Africa, the mountains of Northern Africa. This is the Hogar region, and there's very little data available. It's an unpopulated area. And what we are able to do is actually build up a framework. And we add in the information of what the interpretation was based on, but importantly, we're also adding in details around the confidence that we have in our mapping project, so that the end user can go back and have an insight to how robust the interpretation is, or if there's more data that it would lead to a change in the future. So a lot of the importance behind the structural features is the metadata that dictates and traces the workflow to get to the interpretation, which has taken a long time for the team, but we feel is a very valuable addition to just simply having fault polylines in a map. So with the crust, so we talked a little bit about the thickness of the lithosphere, thickness of the crust. We're also trying to improve our global sedimentary thickness model. Again, the emphasis here is improving data frequency, data quality. The maps above are from the Karoo Basin, onshore southernmost South Africa. On the left-hand side, you can see the global sedimentary thickness grid from Lasky and Masters. This is a grid, just like Crust 1 and Litho 1, that's almost always used in public domain heat flow modeling products. It's astounding how many times research groups pick up these relatively old and out-of-date grids. And these are the products we're trying to make marked improvements upon. On the right-hand side, you can see the constraints from our research, and this has been led by Megan Holt, again from Cambridge. And we're using seismic well data to constrain the sediment thickness. And you can see the wells are the circles and the seismic are the lines on the map. And the differences are obvious. Our data suggests that the basin reaches a maximum thickness of about 9 kilometers. If you compare it to the old grid, that's a significant increase in thickness, should I say. And we're also seeing variations in the architecture of the basin. And this is particularly important in the smaller basins, such as along the East African Rift Valley, because of our improved grid resolution. So again, this is all about improving the understanding of each of these layers, improving the metadata behind, so that when we publish this data, and it will all be free to download to anyone, there's scientific repeatability within these data sets. The end user can understand exactly where the data's come from, the constraints, the techniques used, and the pitfalls, because no data set is perfect in the end. So the reason we spend so much time in trying to improve the quality and the frequency and the understanding of these data sets is because they are inputs to build into thermal inversion models. And the thermal inversion model we are working with is the Vinter-G model. It's being developed by Javier Fuller at the University of Madrid. And I think some people in Northern Ireland will be very familiar with him because he's worked a lot on the island of Ireland doing this similar type of work. The models that he runs have two boundary conditions. One's the air temperature, the other is the 1330 isotherm. He then runs the models to output essentially steady state geotherms for the lithosphere, and he solves multiple 1D conductivity equations. So in essence, the model helps us to understand how heat is distributed within the Earth's lithosphere, considering the mantle's ability to conduct heat at different temperatures and different pressures. And one output that we get from the model is surface heat flow grid, which is incredibly useful, as we can then use that to help predict expected heat flow within, say, sedimentary basins. But then we can also cross-check and validate our lithosphere model against high-quality surface heat flow and borehole temperature data. So what's important with our model and what we've seen in the past is people try and change these lithosphere models to fixed bottom hole temperature data sets. And that's really not what we're looking to do here. In fact, where we identify major discrepancies, it's really important to understand the why. And it may highlight issues with our input parameters into our model. You know, do we need more refinements to our crustal model, our sediment model, our lab? It may highlight an issue with temperature data that we're using. Has it been corrected properly? Is it robust enough? What's the background to that? But it also might highlight a move from pure conductive dominated systems into more convective systems. And this is important because all of what we're doing up to now is really about conductive heat transfer. So where we see anomalies, we can start thinking about convection. So positive anomalies are the discharge of higher temperature fluids, and negative anomalies may represent recharge of fluids or meteoric water coming into a system. So it's really important not to try and force our lithosphere models to these observations, but to use the observations to guide us. So one of the things we need to do to reduce the uncertainty is to make sure that the data we're comparing it to, so the surface heat flow data, is actually really, really valid. And that's another funded project that we're looking into. So we'll talk just very briefly about that. And that's what we're doing with the International Heat Flow Commission. So like me, I suspect many of you have been using this data set for decades, and particularly if you've worked in modeling or for geothermal. And it represents, it's a phenomenal data set. It represents over 60 years of data collection. But there are a number of issues around the data because it primarily relates to the lack of metadata within the data set. And the lack of metadata means that the user can't fully understand the source of data. And the data has been acquired by very different techniques. It uses very different tools, sometimes different depths. Some of the data points, for example, have been averaged from like multiple vertical intersections. Some have been averaged from different locations to perform across the basin. Often data has been extracted from paper journals, but missing metadata. Some data points have been corrected, but actually the correction method hasn't been provided. So using the data in its raw form can be very confusing, but it can also be very misleading. So what we want to do is to utilize the value of the data set and modernize it and apply a system where we can actually account for the quality of the data. So the International Heat Flow Commission, under the leadership of Sven Fox, have been developing a scheme to quality grade the data so that the end user can understand the uncertainty around the data set. And matching the models to this data without understanding its quality could be really misleading, actually. So this process, which is relatively, labor intensive and quite painstaking, will ensure that users in the end will avoid the pitfalls. So we've gone through this process for Africa. We're currently going through this process for North America. And hopefully by the end of in the next 18 months, we'll have covered the globe and updated the database. So that's actually where I want to stop in terms of our research. And I want to kind of just change focus a little bit and give an example of how we can use this type of data as a case study in Northern Ireland. And, up to now you could say, well, this is really nice, Helen, but it's actually very academic. So what? So I'm going to try and convince you of the so what here. So in Ireland, we're really fortunate. We already have this lithosphere model, and it's been through the research endeavours by DIAS, Cambridge, and the University of Madrid, and actually very much has involved a lot of the scientists that are now working for phase 1. And with that background, we have a lithosphere thickness, crustal thickness, and sediment thickness map, and you can see them displayed in a little tiny post-it on the right hand side of the cross section. What we can do with this data is bring it into a lithosphere model. And we can build a model, and the software I'm showing here is one that I use frequently. It's ZetaWare, it's called Trinity and Genesis, or the bolt-on tools. And basically at any given point in Northern Ireland or in Ireland or across the island of Ireland, we can extract the heat flow from the parameters from the mantle, crust, and sediment pile, and sum that together and understand the surface heat flow. And we constrain the temperature at 10 degrees C at the top, because that's the average temperature in Northern Ireland, and we constrain the model at 1330 degrees C, so the isotherm that we talked about that marks the lab. The thickness of the lithosphere and crust that we show are then the thermal properties of those are adapted to reflect our knowledge on crustal density and facies, etc. And we use these output parameters of this model as boundary conditions for our next modeling step, which I want to show. Let's click. So hopefully, so the next step we take for these models, so we've established our thickness of each of our lithosphere parameters, is to QC and output a surface heat flow, is to actually QC this data against borehole data, and to compare the model temperatures with the observations that we have in wells. And I've used the Ballina 1 well up on the north coast due to what is a reasonable depth at TD at 2,600 meters. And most importantly is very high quality bottom hole temperature data. And we input the wellbore tops, the formation thickness, the ages, the lithology, all into the model. And these inputs are really important to understand the impact of conductivity and heat transfer within the sedimentary pile or within the borehole. And you can see the impact of the thermal gradient down the borehole in the middle little plot. The models then run and it outputs a temperature depth profile, which is the black line you see on the left-hand plot. And what we want to do is then compare that output to the corrected measured temperature within the borehole. And when we do that, hopefully this will click on, yep, you can see that actually there's a really good fit with the modeled heat flow from the lithosphere model and what we have observed in the borehole, showing us that actually this is a relatively normal conductive heat transfer, and nothing really should be surprising us here. But we also like to cross-check these models with the additional parameters if we have them. And one of those additional parameters we cross-check these models with is vitrinite reflectance. And this is simply an indicator of thermal maturity of the rock. It reflects the level of heat and pressure conditions the rock has experienced over geological time. We make some assumptions here on the formation and assume that the formation we're measuring has experienced maximum burial, that there's no recent igneous activity. But basically, as organic matter matures under those increasing pressures and temperatures, the structure of the vitrinite changes in a relatively predictable manner. And I say relatively because you have to be a really good expert to do good vitrinite analysis. But those changes are quantifiable, and they can be they color it to the transformation of organic matter into hydrocarbons. And what's really interesting in this well is we see that the vitrinite increase to above 0.6 rho, which is the onset of early generation, we start to see thermogenic gases appear in this well. So when you look at the mud gas parameter, you go from almost no background gas to starting to pick up C1 to C5 within the well. And we equate a 0.6 rho to a temperature of about 85 degrees centigrade. And again, there's a pinch of salt here because it depends on the type of organic matter, etc. But more or less what this is telling us is that even with these individual parameters, whether it's the measured bottom hole temperature, the lithosphere model, the vitrinite, or the background gas, all of this is really behaving in the same way. And it gives us confidence that both the model is correct and the correction of the bottom hole temperature is correct. And this is a genuine depth profile for this area in Northern Ireland and this particular well. So what's important is, of course, that not all wells have the same lithosphere parameters across Northern Ireland. And we know this. We know that up in the north coast, we have slightly thinner crust and different crustal facies due to different Caledonian terrains. So up here in the north, this area in the north where we sampled the well from, the crust appears to be thinner. The contribution from the mantle is therefore slightly higher, but we've modeled this reasonably well in our well. But what happens if we move down to Stormont or Greenmount, where we're running the current demonstrators? Well, here the crust is thicker, the mantle component is less, but thankfully the lithosphere model accounts for all of that. And just this morning I was looking at the Woodburn Forest well, which Rob very kindly shared with me last week, and it's showing slightly lower temperatures for the same equivalent depth and the model is predicting that. So our lithosphere model is holding really well for Northern Ireland. There's no surprises here. And once we have the confidence in that model, we can then start to become predictive away from the boreholes. And we can make predictions on depth surfaces. And I show here, this is in the middle, the top Sherwood, adapted from Rod's map that he created of the top Sherwood. We can input this into the model and get an approximate temperature at the top of this depth map. And you can see that the temperature map more or less follows the contours of the depth map, but you'll also notice it's slightly different to those eagle-eyed amongst you. Maybe you can't read the scale, but it is slightly different to Rob's published predicted temperature map. And we here predicting slightly lower temperatures in and around the Lough Neagh Basin, and of course in these Larne boreholes than we would up at the top. So this is kind of where we get to with the model. One of the next steps that I'd love to do is to input the conductive isotherm in the model that we've got from the Lough Neagh Basin, incorporating the old work and the new work, inputting the new work that's currently being assessed from the demonstrator, and hopefully look at what the top and base of that isotherm is telling us in terms of temperature. But that's probably enough. That is enough for me. Actually, I'm way past my time that I promised Michelle I'd stick to. So basically, that I've kind of said a lot in a relatively short space of time. But if you have any questions, ask, and hopefully you'll get a flavour of how what might seem like relatively academic research actually can be very useful for even understanding small variations in temperatures across the Sherwood in Northern Ireland. So hopefully that's giving you an insight to what we do.